Hello everyone, and welcome to my DDL 2021 presentation. I am Paulo Serra, and this is my presentation about the application of morphological filters in automated imaging for nasal formulations, a design of experiment approach. For bioequivalence studies, the investigation of the critical material attributes is essential in order to prove similarity for the critical quality attributes between RLD and test product. Between the essential critical material attributes for inhalation products, particle size distribution is possibly one of the most important. Particle size distribution is traditionally determined by laser scattering techniques, but can also be determined by automated imaging using an M4ID. The use of automated imaging combined with Raman spectroscopy allows to measure the individual particle size of each component present in a formulation or a mixture. In this case, we have two components, fluticasone propionate and microcrystalline cellulose, typical ingredients in a nasal formulation. For bioequivalence purposes, the particle size distribution of the API is essential to determine. It is then necessary to distinguish the API from the remaining formulation ingredients present in a mixture. In this work, we're going to explore nasal spray formulations. Here we have the case of Flonase, which contains fluticasone propionate and microcrystalline cellulose. In the figure below, you can see that the microcrystalline cellulose can present multiple shapes. Morphological filters can be quite useful in this case. Morphological filters allow to visually differentiate multiple components existing in a mixture and to remove undesirable or not relevant particles from the results. The M4ID software provides us with multiple filters in this case. Elongation. This is the most critical filter that can be used to distinguish between microcrystalline cellulose and fluticasone propionate. As the name says, it measures the elongation of the particle. Circularity. This measures how close the shape of the particle is to a circle. Solidity. This calculates the particle area divided by the area of its convex hull. Convexity. This measures the roughness of the particle surface. Aspect ratio. This works in the opposite way of the elongation filter. As a note, those two filters might not work well together. As last, there are two light-related filters. This measures the light intensity of the particle and can be differentiated as intensity mean and intensity standard deviation. The application of these filters is essential to accurately and efficiently measure and analyze API particles, filtering the excipients and enhancing the efficacy of the measurement. In order to assess all the available filters, a design of experiments was performed. The filters and respective parameters were set in order not to filter out all existing particles of the nasal formulation. This said, limits and a central value were considered for all the experiments. For this design of experiments, only automated imaging was used. Each filter combination was analyzed in triplicate, and different areas of the sample were analyzed. From the results of the design of experiment, it was noticed that several combinations filtered all available particles. Some of the other combinations, they presented a very small number of particles filtering the parameters set. Only one combination presented a reasonable number of particles, taking into account the total number of particles available in the measurable area. To evaluate the success of the design of experiments, the filter set number 10 was further analyzed by Raman to assess the filter's efficiency in separating the different components of the formulation. Each particle detected was chemically identified by Raman, and the obtained spectra was compared with the reference spectra of FP and MCC. The particle size data, combined with Raman, revealed that out of 5,000 particles analyzed, 843 were successfully identified as FP and only 6 identified as MCC. Looking at the particle size data, it can be seen that the FP population, represented as a green line, presents a quite different behavior from the particle size distribution of the overall population if not using any filters. This shows the importance of morphological filters in the particle size distribution analysis of mixtures and to avoid any erroneous conclusions. The efficiency seen in this measurement, 843 particles out of almost 5,000, was still considered good, taking into account the equipment limitations and signal-to-noise ratio. As a conclusion, the work revealed that the design of experiments performed provided a quick screening of the available filters and to create a method to select only API particles for PST measurements. Also, the available morphological filters proved to be a fundamental tool to distinguish between different components in a formulation mixture and to measure their individual morphological properties and also particle size distribution. Through the approach described, we have been able to select the best filters combination, which allowed to manually identify FP particles, as proved by Raman spectroscopy afterwards. If desirable, an optimization of the defined method and the filter's parameters can further improve and increase the method efficiency. In the future, a similar approach can also be applied to study nasal formulations comprising suspended proteins and peptides.